Next definition is called as big omega notation. In big omega notations, our algorithms, that is T of n, is always bounded below by some other algorithms, that is called as g of n, where that g of n is actually a multiple of some constant value called as c. Our algorithms never go below this below line, g of n, when n value is equal to n naught or more than n naught. Okay, now this can be the definition here. A function t of n is said to be in big omega g of n, denoted t of n is belonging to big omega g of n. If this t of n is bounded below by some positive constant multiple of g of n. For all large n, that means n should be very, very large. That is, if there exists some positive constant c and some non-negative integer n naught, such that t of n, means our algorithms, t of n is always greater than c into g of n. This is always smaller than this one. Our algorithm is always greater than this one, when the n value is actually greater than or equal to n naught. At this side, at this area, we are not comparing here. Comparison will be done after a particular constant n value. Okay. Now I can prove it with some example here. Here is an example here. If our algorithm shows a cubic operation like n cube, and we assume that one algorithm is there, its expression is n square, we can say that n cube is always greater than n square. So I can say n cube is actually a cubic operation is belonging to omega n square, when the n value is 0 or more. When the n value is 0, both are same. But when the n value is greater than 0, it's always n cube is higher. We have to understand that here the n is nothing but here the size of the input. We are giving some input to the algorithms. That means n is always some positive value. At least it should be a 1. The n value should be minimum 1. It's always more than 1. Okay. So its n value is never be a less than 0 here. So this condition is true here. N cube is greater than n square. Here the constant is nothing but 1. Here the constant is 1 and n naught is actually just 0 here.